Desalination, how removing salt could quench thirsty nations. In many parts of the world today, turning on a tap is no longer something people can take for granted. Rivers are drying up, underground aquifers are being pumped faster than they can refill. And climate change is making rainfall increasingly unpredictable. Yet just beyond the shorelines of thirsty nations lies an enormous source of water, the ocean. The challenge is simple to describe, but difficult to solve. How do we turn salty seawater into fresh, drinkable water? The answer is desalination, a process that removes salt and other minerals from seawater. Once considered a last resort, desalination is now becoming one of the most important tools for countries facing severe water scarcity. At the same time, it raises serious questions about cost, energy use, and environmental impact. An ancient idea with modern urgency. Desalination may sound like cutting-edge technology, but the idea itself is ancient. Thousands of years ago, sailors already knew that boiling seawater and collecting the steam could provide drinkable water. Ancient Greek thinkers such as Aristotle observed that when salty water evaporates, the salt is left behind. Roman engineers experimented with clay filters, and Chinese civilizations noticed that thin films forming on bamboo mats could trap salt. For centuries, these methods remained small-scale and were used mainly for survival at sea. It was not until the 20th century, when populations surged and water demand skyrocketed, that desalination began to develop into a global industry. Today, more than 300 million people rely on desalinated water every day. And over 20,000 desalination plants operate worldwide. How desalination works. Modern desalination plants typically rely on one of two main methods. Thermal desalination mimics the natural water cycle. Seawater is heated until it evaporates, leaving salt behind. The vapor is then cooled and condensed into fresh water. While reliable, this method requires large amounts of heat energy, making it expensive unless low-cost energy is available. The second and most widely used method is reverse osmosis, RO. In this process, seawater is forced at very high pressure through a semi-permeable membrane. These membranes are so fine that they block not only salt, but also bacteria and viruses, allowing only pure water molecules to pass through. As a result, desalinated water is exceptionally safe to drink. Reverse osmosis uses less energy than thermal methods, and now accounts for about 70% of global desalination capacity. Thanks to advances in membrane materials and energy recovery systems, the amount of energy required to produce fresh water has dropped dramatically since the 1970s. The true cost of fresh water. Although desalination provides a reliable source of water, it comes at a cost. Producing desalinated seawater typically costs between 50 cents and $1 per cubic meter, depending on location, energy prices, and technology. By comparison, traditional groundwater or surface water often costs only a fraction of that amount. This price difference explains why desalination was long considered a last resort. For many regions, it was simply too expensive for everyday use. However, as freshwater supplies become less dependable and desalination technology improves, many governments now view it as a necessary investment, one that may be far less costly than the consequences of running out of water altogether. Where desalination is making a difference. Some countries have embraced desalination so fully that it has reshaped their entire water systems. Israel is one of the most well-known examples. Facing limited rainfall and rising demand, the country invested heavily in coastal desalination plants. Today, desalinated seawater supplies most of Israel's drinking water, and has even helped stabilize natural reservoirs. In the Middle East, desalination is often essential for survival. Countries such as Saudi Arabia and the United Arab Emirates have few rivers and minimal rainfall. Yet they support large urban populations. Massive desalination plants provide water for cities, industries, and agriculture. Desalination is also expanding beyond traditionally arid regions. Singapore, for example, uses desalination as part of a broader strategy. That includes rainfall capture and wastewater recycling. In California, desalination plants serve as backup supplies during severe droughts, offering an added layer of water security when other sources fail. The environmental trade-off. Despite its promise, desalination is not without environmental costs. One major concern is energy use. Desalination is energy-intensive, and when powered by fossil fuels, it can increase greenhouse gas emissions, contributing to climate change, which in turn worsens water scarcity. Another serious issue is brine, the concentrated waste left behind after desalination. Brine is not simply salty water, it forms a hypersaline plume that is often oxygen depleted, and may contain chemicals such as chlorine or anti-scalants used to clean pipes and membranes. If released improperly, this dense plume can sink to the seafloor and harm marine ecosystems. Seawater intake systems can also affect marine life. Fish larvae and plankton may be trapped when water is drawn into desalination plants, disrupting local food webs. Smarter, cleaner solutions. To address these challenges, engineers are redesigning desalination systems to be cleaner, safer, and more efficient. High energy use is being reduced through solar and wind power, along with energy recovery devices that reuse pressure from the desalination process. Marine life harm is minimized through subsurface intakes that draw seawater through sand and seabed layers, naturally filtering out organisms. Brine waste is being reimagined through brine mining, which extracts valuable minerals such as lithium and magnesium, instead of releasing waste into the ocean. Looking further ahead, researchers are developing emerging membrane technologies, including filters made from graphene, a one-atom-thick form of carbon. These ultra-thin membranes could allow water to flow much faster than current reverse osmosis systems, while still blocking salt, bacteria, and viruses. If produced at scale, graphene membranes could make future desalination plants faster, more energy efficient, and less expensive. Other innovations include deep-sea desalination, which uses natural ocean pressure to reduce energy needs, and compact solar-powered systems, designed to supply water to remote or off-grid communities. Is desalination the ultimate answer? Most experts agree that desalination should not replace water conservation, efficiency improvements, or wastewater recycling. In many cases, reusing water or reducing waste requires far less energy than desalinating seawater. However, in regions with little rainfall, limited freshwater sources, or rapidly growing populations, desalination may be the only dependable option. As costs continue to fall and technologies advance, it is becoming a more realistic solution for an increasing number of communities. A future shaped by choice. Desalination shows how human ingenuity can transform an immense challenge into an opportunity. Turning seawater into drinking water once seemed impossible. Today, it sustains entire cities. Yet the technology also reminds us that every solution involves trade-offs. If powered by clean energy and managed responsibly, desalination could help secure water for future generations. Used carelessly, it could damage the very ecosystems it depends on. In a warming, increasingly thirsty world, removing salt from seawater may not solve every problem, but combined with conservation, innovation, and respect for nature, it could help quench the thirst of nations standing at the edge of the sea.
It's time to study new words in context. 1. Quench. Definition: to satisfy a strong need, especially thirst, by providing something essential such as water. Example: clean drinking water can quench the thirst of communities suffering from drought. 2. Take for granted. Definition: to assume that something will always be available, or unchanged, without appreciating its value. Example: many people take clean tap water for granted until shortages begin. 3. Aquifer. Definition: a natural underground layer of rock or soil that stores and supplies groundwater. Example, overuse of the aquifer caused water levels to drop faster than they could recover. 4. Cutting edge. Definition, extremely modern and advanced. Representing the newest developments in a field. Example, desalination plants now use cutting-edge technology to improve efficiency. 5. Mimic. Definition, to copy or imitate how something works, often in order to achieve a similar result. Example, thermal desalination mimics the natural water cycle of evaporation and condensation. 6. Semi-permeable. Definition, allowing some substances to pass through while blocking others. Example, a semi-permeable membrane lets water molecules through but blocks salt. 7. Membrane. Definition, a thin material layer that separates substances by filtering specific particles. Example, reverse osmosis uses a membrane to remove salt and impurities from seawater. 8. Arid. Definition, extremely dry, with little rainfall and limited natural water sources. Example, many arid regions rely on desalination to meet their water needs. 9. Brine. Definition, highly concentrated salty water left over after freshwater has been removed. Example, desalination plants must carefully manage the brine produced during the process. 10. Hypersaline plume. Definition, a dense flow of extremely salty water that spreads underwater, often after being released into the ocean. Example, if not properly dispersed, a hypersaline plume can damage marine ecosystems. 11. Depleted. Definition, reduced greatly in amount or strength due to heavy use or loss. Example, the region's groundwater supply became depleted after years of overuse. 12. Scalant. Definition, a chemical substance that prevents mineral buildup inside pipes and membranes. Example, anti-scalants are used to keep desalination membranes from clogging. 13. Larva. Definition, the early developmental stage of animals such as fish or insects. Example, fish larvae can be harmed if they are drawn into desalination intake systems. 14. Reimagined. Definition, rethought and redesigned in a new or more effective way. Example, engineers have reimagined brine as a resource rather than waste. 15. Graphene. Definition, a one-atom thick layer of carbon, known for its strength and ability to filter water efficiently. Example, graphene membranes could make desalination faster and less energy-intensive. 16. Off-grid. Definition, operating independently without connection to public electricity or water systems. Example, off-grid desalination units can provide clean water to remote coastal villages.
Comprehension questions. 1. What problem does the article identify at the very beginning? Answer. The article explains that many regions are facing water shortages because rivers are drying up, groundwater is being overused, and climate change is making rainfall unpredictable. 2. What is desalination? Answer. Desalination is the process of removing salt and other minerals from seawater to make it safe for human use, especially drinking. 3. Why was desalination once considered a last resort? Answer. It was considered a last resort because it required large amounts of energy and was much more expensive than using rivers, lakes, or groundwater. 4. How far back does the idea of desalination go? Answer. The idea dates back thousands of years to ancient sailors, Greek philosophers like Aristotle, Roman engineers, and Chinese civilizations. 5. What major change in the 20th century caused desalination to expand globally? Answer. Rapid population growth and increasing water demand pushed societies to develop desalination on a large industrial scale. 6. What are the two main methods of modern desalination? Answer. The two main methods are thermal desalination and reverse osmosis. 7. How does thermal desalination work? Answer. It heats seawater until it evaporates, leaving salt behind, and then condenses the vapor into fresh water. 8. Why is reverse osmosis the most widely used method today? Answer. Reverse osmosis uses less energy than thermal methods and is highly effective, making it more efficient and cost-effective. 9. What makes reverse osmosis membranes especially effective? Answer. They are so fine that they can block salt, bacteria, and viruses, allowing only pure water molecules to pass through. 10. How much does desalinated water typically cost compared to traditional water sources? Answer. Desalinated water usually costs between 50 cents and $1 per cubic meter, which is more expensive than groundwater or surface water. 11. Which regions rely most heavily on desalination today? Answer. Israel, the Middle East, especially Saudi Arabia, and the UAE, Singapore, and parts of California rely heavily on desalination. 12. What is brine and why is it an environmental concern? Answer. Brine is the concentrated waste left after desalination. It forms a hypersaline, oxygen-depleted plume that can harm marine ecosystems if released improperly. 13. How can desalination plants harm marine life during water intake? Answer. Small organisms like fish larvae and plankton can be trapped when seawater is drawn into the plant, disrupting local ecosystems. 14. What are some innovations that reduce desalination's environmental impact? Answer. Innovations include renewable energy use, subsurface intakes to protect marine life, energy recovery devices, and brine mining for valuable minerals. 15. What is graphene and why is it important for the future of desalination? Answer. Graphene is a one-atom thick form of carbon. Graphene membranes could allow water to flow faster while using less energy, making desalination cheaper and more efficient. 16. Why do experts say desalination should not replace conservation and recycling? Answer. Because conserving water and reusing wastewater usually requires much less energy than desalinating seawater. 17. What is the main message of the article's conclusion? Answer. Desalination is a powerful tool, but it must be used responsibly alongside conservation and clean energy to ensure a sustainable water future.